Assalamualaikum warahmatullahi wabarakatuh. So today I want to share about our project is gardening hoe. The introduction of gardening hoe is the widely used hand tool for soil cultivation and weeding. Although the design is very simple, it's inspiring in a bending force during use because the apple for is not aligned with the handle. So this creates a bending moment, especially at the joint between the wooden handle and the metal head, which is it must be critical region for the failure. Understanding a bending stress, material properties, and handle geometry is important to ensure the hull is very strong, safe, and durable during the repeated use.
So now I will talk about problem statement. A hoe experiences bending force during use, producing bending stress that can lead to deformation or failure. Second, the handle may act as a cantilever, simply supported or overhanging beam, each creating a different stress distribution. Next, many existing hoe design do not consider this beam condition, causing high stress concentration at critical areas. And last one is a bending stress analysis using solid mechanics is needed to improve the safety and durability of the hoe.
So, the objective of the project is to understanding the basic principle of the bending stress or in a gardening home. So, the second is to analyze the effect of the bending moment and external force of the whole handle. And the third is to study how the material properties and handle shape affect a bending behavior. So the last is to determine the structure of the strength and the safety of a gardening hole using a bending stress theory. So the project scope of the gardening hole is the first is analysis of the bending moment and the bending stress in the hole handle. The second is study of tensile and compressive stress to distribute across the handle in a cross section. The third is investigation of the effect of the handle, leg, apply force, and material type of reflection. So the lastly is the dynamic load, where and critical and the corrosion are not be considered.
Now I will talk about related literature review. So the first one is bending stress and beam theory. Bending stress occurs when a beam is subjected to a bending moment. One side experience tensile stress, while the opposite side experience compressive stress. And stress magnitude depends on load, geometry, material properties, and support condition. Okay. Next is cantilever beam in hole application. So a fixed at one end and free at the other. Second, produce maximum bending moment at the fixed end. At the fixed end. In hole usage, the highest stress occur near the blade handle joint. Next is simply supported beam in hole handling. Supported at 2 points and allowed to rotate. Second, produce lower maximum bending stress than a cantilever beam, and stress is more evenly distributed, improving durability and comfort. Next is overhanging beam and stress distribution. So beam extend beyond the support point, creates complex bending moment and stress concentration, and overhang section may reduce handle durability if not properly designed.
Assalamualaikum warahmatullahi wabarakatuh. My name is Mia Humaira binti Rosdi. My matrix number is AA240525. In this video, I will explain the workflow used in our project from the initial idea until the final implementation and presentation. So first, we start with product selection and identification. At this stage, we decide what type of product or structure we want to design and analyze. This helps us clearly understand the function of the product and the problem that we aim to solve. Next, we move to the material selection and dimension measurement. Material selection is important because different materials have different strength, stiffness, and durability. At the same time, we measure and define the dimensions of the product such as length, width, thickness, or diameter depending on the design. Both of these steps lead to the problem formulation. Here, we define the engineering problem clearly including the loading conditions, constraints, assumptions, and objective of the design. After that, we proceed to engineering modeling. In this step, the real structure is simplified into an ideal engineering model so that analysis can be done more easily. We can classify the structure into one of three common beam types, which are cantilever beam, simply supported beam, or overhanging beam. This classification is important because each type has different support condition and behavior under load. Next is solid mechanics analysis. Here we analyze how forces act on the beam and how the beam responds to those forces. From this analysis, we construct the shear force diagram and the bending moment diagram. These diagrams help us understand where the maximum shear force and the maximum bending moment occur in the structure. Using these results, we perform the necessary calculation such as stress, fraction, and factor of safety to check whether the design is strong and safe enough. Then we move to the design verification. At this stage, we evaluate whether the design meets all the requirements and safety criteria. If the design is not acceptable, we go back to the calculation stage and make improvements. If the design passes verification, we proceed to the next step. After verification, we continue with the digital implementation. This includes creating the design using software tools such as CAD or SolidWorks simulation software to visualize and validate the final structure. Finally, we complete the process with recording and video presentation where we document the design, analysis process, and final results. And with that, the project workflow comes to an end. Thank you.
For this section, the proposed solution is to analyze the structural behavior of a normal flat garden hoe using bending moment principle from solid mechanics. During gardening activities such as digging and soil loosening, force applied at the handle produce bending along the hoe. This bending may cause high stress, especially along the handle and the black handle joint. Okay, so to represent realistic usage, the hoe is analyzed under three bending conditions. The first one is cantilever beam, second is simply supported beam, and the third one is overhanging beam. Each condition reflects different ways the hoe is supported and loaded during use. By studying the bending moment pattern under this condition, critical stress region can be identified. The results from this analysis are then used as the basis for proposing an improved design that enhances strength, safety, and durability while maintaining practical usability. Okay, so for this project design stages, we explain how the analysis is carried out step by step. First, a normal flat garden hoe is selected as the case study. Its straight handle and flat blade allow it to be reasonable model as a beam, making it suitable for bending moment analysis. Next, the bending condition experienced during use are identified. These include cantilever, simply supported, and overhanging beam condition, which help represent realistic support and loading scenario. After that, free body diagram are prepared to show applied force, reaction, and load direction. This diagram simplify the understanding of force distribution and bending behavior. Finally, critical regions are identified based on bending moment trend. This allows design improvement to be planned, especially the area prone to high stress, such as the blade handle joint.
So we move on to the next part, which is relevant calculation bending moment analysis. This section evaluates the structural strength of the proposed hoe design using mechanical analysis. The goal is to ensure the tool can safely withstand normal gardening loads without failure or permanent deformation. So firstly, data analysis. From the design, we can exploit some details, which is the length of the hose handle, blade, and maybe make assumption for load. For handle length, the length of the handle is about 1150 millimeter. The material used is aluminium alloys alumina. As for the diameter of the handle, which is 50 millimeter, and so the blade. For the blade, the diameter of the blade is 60 millimeter, and the material used on the blade is cast carbon steel. And we assume the load on the beam around 200 Newton. So for the second part is idealization. So the picture on the slide shows the diagram of overhanging beam model. So as you can see, the length of the beam about approximately 1150.01 millimeter. Okay, so at the point 8 there is a spin support, and at point B there is a support, roller support. So the distance between point A and point B, which is the fulcrum point B, the lower hand placement on the hole is about 450 millimeters. So the first step to the calculation, which is bending moment calculation. So firstly, we need to find the reaction forces. So using the sum of moment about point A, so we gather the information and do the calculation, and then we got the RB value, which is 511.12 Newton. So, and then using the sum of vertical forces, Fy, and then we do the calculation, and then at the end of the calculation we will get the value of reaction A, which is negative 311.12 Newton. The negative sign indicates the top hand pushes downward. So the second step is we need to find the maximum bending moment. So the maximum bending moment occurs at the fulcrum point B, where the handle is most likely to bend or break. So regarding to our hole design, our gardening tools, so to find the maximum bending moment, we need to multiply the force and distance from the pivot. So we do the calculations, and the maximum bending moment we will get approximately around 140,000 Newton millimeter, or we can use Newton meter as unit, which is 140 Newton meter. So the next part is stress analysis, checking strength. So using design diameter of 60 millimeter, we need to find the value of section modulus. So as you can see on this slide, the formula given is pi multiplied with diameter cube over 32. So we substitute the value, the given value, and then we will get approximately around 21,250.75 millimeter cube. So after we calculate the section modulus, we move on to the maximum bending stress, which is bending moment, maximum bending moment divide with the section modulus. So we do the calculation, and the answer we will get around 6.60 megapascal. So for analysis of shear force and bending moment diagram, in this analysis, we are examining the internal forces of a beam member across its total length of approximately around 1,150 units, 50 millimeters. By comparing the shear force diagram and the bending moment diagram, we can identify the types of loading applied and the location of maximum stress. So we move to the shear force analysis. Looking at the shear force diagram in figure 3.2, the diagram shows a constant negative shear of approximately around negative 311 11 kilonewton from the start of the beam to the 450 millimeter mark. At exactly the 450 unit mark, there is a sharp vertical jump in shear force. This instantaneous change indicates the presence of a large point load, concentrated load acting upward at this location. From the 450 mark to the end of the beam, the shear remains constant at positive 200 kilonewton. As for bending moment analysis, in figure 3.3, the bending moment starts at 0 at both ends, which is typical for a simply supported beam. The moment decreases linearly to reach its peak negative value. The maximum bending moment occurs at the 450 unit mark, precisely where the shear force crosses the zero axis. The peak magnitude is approximately around negative 140,000 kilonewton per meter. Because the diagram consists of straight, sloped lines rather than curves, we can confirm that the beam is subjected to point loads rather than distributed loads. So, for the completion and structure implications, in summary, the 450 unit mark is the most critical section of this beam. It experiences the highest internal bending stress and the most significant transition in shear force. Engineers would use these peak values around 200 to 310 kilonewton for shear and 140,000 kilonewton meter for moment to verify that the beam material and cross-section can safely support the applied loads.
For the final purpose design, the improvement is not based on appearance but on the bending moment analysis discussed earlier. From the three beam conditions, overhanging, cantilever and simply supported, we identify that the highest bending moment occur near the blade handle joint, especially under cantilever loading during soil penetration. Therefore, the purpose design focus on strengthening this critical region by reinforcing the joint and ensuring a smooth transition between the blade and handle to reduce stress concentration. The handle geometry is designed to promote more uniform stress distribution when bending occurs, while the overall length is maintained to avoid excessive bending moment during use. This design ensures the hoe can withstand realistic gardening loads when more safely and durably, while still maintaining practical and easy to use.
Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. My name is Siti Nur Aini Binti Agus Ramli. My metric number is AA240881 and I'll be presenting about safety, health and environmental consideration. There are four aspects, which is safety, health, environmental and public interest. Safety, the hole that we created, the handle designed to withstand bending and impact forces. Secure blade handle joint to prevent detachment. Proper blade finishing to reduce risks of cuts. Blades weight a suitable handle length for better control, which is the hole that we design properly and precisely to eliminate any possible risks and hazard. The handle design so it won't bend for the huge force act upon them, and then the secure blade is preventing from any cuts from slippage during the usage, and proper blade finishing. For example, it not too sharp and it only sharp enough to cut through the soils and the balance weight so it's not slip during the when we lift them. For health, ergonomic design to reduce muscle fatigue, which are we will put a good stick or good handle to prevent from the muscle soreness, and a suitable tool weight to minimize physical strain. if it too he- if it's too heavy, it will hard for the users to lift it and use it. Comfortable grip to prevent hand blister and hand pain. So, if the surface of the handle is too rough, the possibility to have blister on the user's hand are high. We move on to environmental aspect. Manual operation, no fuel or electricity required, which this hole won't be used any petrol that will create carbon dioxide or electricity required, which save our money from using or electricity. Recyclable material, steel blade and wood handle. Both of this part is recyclable if the whole break. So we can get a new one and the old one we can recycle. And then durable design, reduce waste and replacement. So for example, the design required only few steps and we don't have to um, cutting or cutting through it, cutting of some materials to create a precise design. So it's just simple and we don't have any material usage, material wastement. And then lastly, public interest. It's safe and easy to use for general users, improve food efficiency and users' comfort, responsible design, reduce injury risks. Okay, that's all from me. Thank you.
This is our whole drawing design. For the handle length is around 1500 millimeter and the handle diameter is around 25 millimeter. Blade size is 130 and 150. The blade thickness is around 5 millimeter. This whole design is used for loosening soil, removing weeds, shaping soil beds, and light digging while allowing the user to work in a standing position to reducing bending and fatigue. The whole material is using ductile iron and while the handle we use oak wood.
And then for the material selection, we choose material based on strength, durable, and safety. So material selection is important. To ensure the garden hoe is strong, durable to safe and safe to use. And then each patch of the garden will experience different force during use, especially bending force. So, suitable materials are important to avoid fail, failure and increase stall performance. And next about handle and blade material. For the handle, we can see we choose the aluminium and we choose aluminium because for the handle we choose aluminium because it lightweight but still strong enough to withstand bending stress. And based on our bending stress analysis, the stress on the handle is within the safe limit. And aluminium is also corrosion resistant, which make it suitable is for outdoor use and reduce user fatigue. fatigue. And next about the blade material, we choose the carbon steel. And for the blade, carbon steel is selected because it's a high stretch and harder. And because of that, the blade experience impact the compressive force during digging. Carbon steel also carbon steel can withstand the force and has good wear resistance, which make the blade durable and effective. And last about grip material. For the grip material, rubber or polymer is used to improve comfort and safety. This material also provide better grip and prevent slipping during use. It also reduce vibration and high fatigue when the tool is used repeatedly. And for the conclusion, in conclusion, the selected materials have improved the strength and durability and safety of the garden home based on solid mechanic principle.
This study shows that a gardening hoe experienced significant bending stress during normal use. Modeling the handle as a cantilever, simply supported and overhanging beam revealed that stress and deflection vary with handling condition, with the highest stress near the blade handle joint. Handle length, applied force, and material properties strongly affect deflection and performance. Bending stress theory and beam analysis are therefore essential for designing a safe, durable, and efficient hoe.